Hello dear colleagues, I'd like to briefly present you some considerations on and models for digital twin implementation in smart manufacturing systems, which may be of importance for smooth and efficient development industry of 5.0. The very concept of Industry 5.0 emphasizes enhanced collaboration experience, which is to be ensured by improved human-machine interaction. Digital twins are widely used as human-machine interfaces and control units in various spheres. Smart manufacturing systems have to be collaborative manufacturing entities able to respond in real time to conditions and demand changes. Such communication of production system units is also a characteristic feature of digital twins, which are representation of physical elements, usually using Internet of Things and sensor data to monitor operations, control physical elements, and support decision-making process. To acquire data, analyze and optimize energy consumption of a smart manufacturing production, for which material flows, data flows, particular processes are shown in this figure, design and deployment of analytical platform is absolutely fundamental. We have developed a classification of data types collected and used in smart manufacturing, specifically for purposes of digital twin development and use. This is shown in this slide and detailed in our paper. It is crucial to put in place data management system for the purpose of storing and managing energy data scenarios, consumption, managing production parameters, etc. By gathering data, identification of the most energy-consuming aspects of particular process will be possible, which will then facilitate the integration of new digital technologies, distributed procedure management, data part optimization. In order to determine the energy-intensive processes or equipment, it is necessary to gather data on energy consumption, production and efficiency using specifically selected smart sensors, meters and other monitoring devices. Algorithms can improve the machine's performance to consume less energy by assessing data on operating parameters and the amount of material being used. Based on these data obtained from the set of embedded sensors and external data generators, reference matrix would be developed needed to mathematically describe each process and its dependencies. Target function built on this dataset may serve as a tool for optimization of the process. Optimization schema is shown to the left on figure 4, and to the right we have some business-oriented schematization. Here inputs X and outputs Y are the quantities characterizing material and information flows, and the control signal U is to be optimized and actually represent the solution optimization problem. Solving the general optimization problem is quite complicated, as it comprises functional relations of different types for numerous variables of various nature. However, the equations describing particular process contain only variables characterizing that particular process. Therefore, it allows a decomposition, shown here, and construction of the optimization recipe as a superposition of partial solution for separate subsystems. And for the optimization purpose, we constructed Lagrange polynomial, which contains variables and control parameters, and developed a sequence of steps. In the first stage, we calculate the output vectors Y, and in the second stage, the system of equation is to be solved to correct iteratively those output vectors Y for each subsystem. The conditions for interruption of this iterative procedure depends on the chosen tolerance parameter, and solution is then corrected on a higher level of the optimization. That higher level corresponds to the overall system management. Augmented reality enhanced digital twins will facilitate greatly human-computer interaction, and one of the bottlenecks of this technology is production of the proper implementation, full range of interaction between physical space and virtual twin. So we propose the sequence of steps represented in this figure to develop such. Information is an important asset for every business, therefore it requires proper design and developing of security level, and following the STRIDE methodology we identify types of security threats and also propose the countermeasures for each of them. These can be directly implemented and are to be strictly followed in software component development and design. Here are our conclusions. Thank you for your attention.